everyone and welcome back to my channel. In today's video, we are going to solve a very practical problem. We are looking at the Chinese Postman Algorithm, a mathematical way to find the shortest route that covers every single road in a network. Let's dive in. So, what is this all about? Imagine a postman starting their day at the depot. They have to deliver mail to every single street in their neighborhood. And at the end of the day, they have to drive back to the depot. The question is, how do they cover every road but drive the absolute shortest total distance? By the end of this video, you will understand exactly what the Chinese postman algorithm is, the difference between Eulerian and non-Eulerian graphs, and most importantly, how to modify a graph to find that perfect shortest route using a simple 7-step process. Before we dive into the math, let me clearly outline what we are going to cover in this video. First, we will understand exactly what the Chinese postman algorithm is and what problem it actually solves. Next, we need to revisit two important graph theory concepts, Euler Trail and Euler Circuit. They are the mathematical foundation that make this algorithm work. So it's crucial we understand them. Then we will discuss its purpose. Why do we actually need this algorithm in the real world? After that, we will look at the difference between Eulerian and non-Eulerian graphs. And most importantly, we will learn how non-Eulerian graphs are modified so they can be solved. Finally, we will tie everything together with a simple step-by-step example so you can see exactly how the algorithm works in practice. Let's get started. So, what exactly is it? Formally, the Chinese postman algorithm finds the shortest closed route that visits every single edge of a graph at least once. The keywords here are shortest, every edge, and closed route. We don't just want to walk randomly, we want to optimize the total distance while making sure we return to where we started. Why do we actually need this algorithm? Let's break it down into three core purposes. First, 100% coverage. Every single road must be visited at least once, no missed deliveries. Second, minimize cost. We need to find the shortest possible total distance to save time, fuel, and money. Third, return to start. The route must end where it began. A closed loop so the postman gets back to the depot. Look at this comparison. Without the algorithm, the postman walks randomly and backtracks too much, wasting a total distance of 34. But with the algorithm, we follow an optimized loop with minimal backtracking and the total distance drops to just 26. That's massive saving. This is exactly why we need this algorithm. This problem was introduced back in the 1960s by a brilliant Chinese mathematician named Mei-Ko. That's why it carries the name Chinese postman. In the academic world, it is also formally known as the route inspection problem, and it remains a classic example of graph theory applied to the real world. Before we go further, let's do a quick refresher on graphs. A graph is simply made up of vertices and edges. Think of the vertices as intersection or locations and the edges as the road connecting them. In our case, each edge has a width which represents the distance or cost of traveling down that road. In this example, the edge between A and B has a distance of 5. To understand the Postman problem, we first need to understand the legendary mathematician Euler. And Euler Trail is a trail that uses every single edge of a graph exactly once, no repeats and no skippings. Simply enough, right? But there is a catch. Euler Circuit takes it one step further. It uses every edge exactly once. It starts and ends at the exact same vertex. Why is this so important for us? Because our postman needs to return to the starting point and the end of the day. If a graph has an Euler circuit, our postman can cover all roads exactly once without any backtracking. Perfect, right? But as we'll see, that's rarely the case in real life. Here is the golden rule of graph theory. A graph is Eulerian if and only if every single vertex has an even degree. If all vertices are even, we have Eulerian circuit and the postman's job is easy. However, if the graph has any vertices with an odd degree, it is non-Eulerian. You cannot draw a circuit without a repeating edges. Real world road networks almost always have odd vertices, which is why we need this algorithm to fix the problem. Here is the master plan. We are going to follow exactly 7 steps to solve this. First, we list all the odd vertices. Then we pair them up, find the shortest paths between those pairs, and choose the cheapest pairing. After that, we duplicate those select edges, calculate the new total width, and finally we need the Eulerian circuit. Let's apply these 7 steps to a real example so you can see it in action. Take a look at this graph. We have 5 vertices A, B, C, D, E. Let's quickly calculate the degree of each vertex. Vertex A connect to B and C. That's degree 2, that's mean even. Vertex B connects to A and D. Degree 2, that is also even. Vertex C connects to A and D. Degree 2, that means it also even. Vertex D connects to B, C and E. That's degree 3. That's the odd one. Vertex E only connects to D. That's degree 1. That means it is also odd degree. Since we have 2 odd vertices, D and E, this graph is non-Eulerian. We need to fix it. Let's begin step 1. Step 1 is done. We have identified our odd vertices. They are D and E. Let's move to step 2. Step 2 is to list all possible pairing of these odd vertices. Since we only have 2 odd vertices, D and E, there is only one pairing. Just pair D with E. If we had 4 odd vertices, we would have multiple pairing options, which we would have to compare later. But in this case, it's simple. Alright, step 3. We need to find the shortest path between our 2 odd vertices. D and E. How do we do that? Let's look at the graph. Is the shortest path option true? D to C, C to A, B to D, and then D to E. Wait, look at this. We went all the way around the graph and came right back to D before finally going to E. That's just a big loop that returns to where we started. Let's add it up. 2 plus 4 plus 5 plus 3 plus 6. That gives us 20, right? No. This one is wrong. We don't want to waste time going in circle. Okay, what about this one? In option 1, D to B, B to A to C, C to D, and D to E. Again, we did the exact same thing. We looped all the way around and came back to D again. Before heading to E, let's do math. 3 plus 5 plus 2 plus 4 plus 6. That's also 20. No problem again. Both of these options are terrible. They cost us 20 units of distance and they don't even make logical sense for a postman. So if those are wrong, what about this one? Just look right here. D and E are directly connected by a single edge. No loops, no backtrackings, no going in circles. The weight of this edge is simply 6. Is it this one? Yes, this is the one. The shortest path between D and E is the direct edge with a weight of 6. 4 is to find the minimum sum. Since we only have one pair in D plus E, the total is simply 6. If we had multiple pairings, we would add up the weights of each path in the pairing and choose the smallest total. But here, the minimum sum is 6. We have selected the path between D and E. Now step 5. We modify the graph. We take the path we selected, which is the D to E edge, and we duplicate it in your diagram. You will see this duplicated edge drawn as a dashed line running parallel to the original, right? Why do we do that? Because adding this edge increases the degree of the both D and E by a 1. D was degree 3, now it becomes 4. Even. E was degree 1, now it becomes 2. It also even now. Suddenly our non-Eulerian graph has become Eulerian. All vertices are now even, which means we can finally draw a circuit. Step 6 is simple math. Let's add up all the original edges. A to B is 5, B to D is 3, A to C is 2, C to D is 4, and D to E is 6. That totals of 20. We added one duplicate edge, D to E, which is 6. So, 20 plus 6 give us a grand total of 26. This means the postman will have to travel a total distance of 26 units to cover every road and get back home. Finally, at step 7, we find the actual route, the Eulerian circuit. Starting at A, we go to B, then from B to we go to D, from D, we take the original edge of to E. Now we have to come back, so we take the duplicate edge from each back to D. From D we go to C, and finally from C we go to back to A. This is the route is. Uh, let's check the edges: A to B, B to D, D to E, E to D. That's duplicate one. D to C and C to A. We use every original edge exactly once, and we used a duplicate edge to make it back perfect. And there we have it, our final result. We have successfully covered every single edge in the graph. We added the absolute minimum exact trouble required, just that one duplicated road, and our route returns perfect to the starting point. The optimal total distance for our postman is 26. While we call it the Chinese postman problem, this algorithm is used everywhere in the real world. It's used for postal delivery and mail sorting, but also for the garbage collection trucks, street sweeping, and snow plowing, planning delivery routes for the logistic companies, and even road inspection for pothole or and damages. Whenever you have a vehicle that needs to cover a specific set of parts and return to base, this algorithm saves massive amounts of time and fuel. I hope this presentation helped you understand the Chinese postman algorithm in simple and practical way. Thank you for listening.